start with exactly the same example matrix that we started with yesterday.
Okay.
And so we had a system of three equations and three unknowns that represented planes.
Yep.
And we found out the intersections of those planes where x was 1, y is 2, z is 3. And what we did was we got this into reduced echelon form, and we found out that z was 3. And then we just back substituted into the other equations. We obtained a value for y, and then we used the z and y, and we obtained a value for x using equation 1. Okay, there's a second form of reduced echelon form, and that's called row reduced echelon form. And not a whole really weird concept. It's just taking this and actually getting it explicitly in terms of x and y and z.
Okay.
So this is where we ended yesterday. All we really need to do to get this into row reduced echelon form is get this main triangle and the upper triangle both to be 0. Okay, so what we're going to do, let's start out in row 2, just so that you can see where we're going at. I want to get rid of the -1 here where the z is, and I'm going to do that by taking this row 2 and adding row 3 to it. Okay? Because everything is 1, I don't have to do any fancy multiplication. Row 3 is fine as it is. It's beautiful. We like it as it is. Row 2 is going to become 0, and 1 plus 0 is 1. And -1 plus 1 is 0, and that was what I was after. I was after a 0 right there. And -1 plus 3 is 2. So in doing this operation, I've eliminated the coefficient that goes with z normally.
Yep.
And right now I can actually read that y is equal to 2. And we're also going to eliminate the z from the top row as well while we're doing this. And we can do that just by taking row 1 up here and subtracting row 3.
Okay.
This example might be a little less than instructive because everything is 1. Like if this was a 2 up here, I'd have to subtract 2 times row 3.
Yeah. Okay, so we can multiply them by scalars then?
We can multiply them by scalars, okay? And that way we can get rid of the numbers if they're not 1. So
it's just like just in more of a formatted sort of thing. Can you hear me?
What's that?
It's just like elimination, sort of.
It's exactly like an elimination, yeah. Like if this was a 5, I'd be subtracting 5 times row 3 from row 1. So yeah, I realize now maybe it's not the best example, but boy, it's sure easy.
It is.
So I'm going to take row 1 and I'm going to subtract row 3. Okay, so I end up with 1, and -1 minus 0 is -1, and 1 minus 1 is 0, and 2 minus 3 is -1. Okay, so we're not quite in the full row reduced echelon form yet, because in the top row, I still have an entry here where the y is.
Yeah. So are we
Spencer?
Sorry.
You're helping with Mr. Ferguson with the trailer today. Okay. All right. Little outtake there.
Sorry.
All right.
Are we just trying to find, so in the top row, we want the x value to be 0 or 1? Or,
that's right.
So we're just trying to eliminate the other variables from, so for row 1, you want the x. For row 2, you want the y. And for row 3, you want the z?
That's exactly right. Yes, that's the whole objective right there. We want to be able to read x is equal to this number, y is equal to that number, z is equal to that number. And we'll know we've got that when we got all zeros here and all zeros there. Perfect.
Because that's just stating that, like for second column, for example, like 1y equals 2.
Exactly. Yeah. That's all it is. Perfect. Not terribly abstract.
No.
It actually makes it, just looking at it makes it seem more abstract.
Yeah.
Okay. I'm going to throw this out to the audience. How can I get rid of this -1 right here?
Add row 2.
Yes, add row 2.
Okay.
And once again, maybe not an instructive example because it's just ones.
Yeah.
But boy, it's sure easy. I like that. Okay, so we're going to be taking row 1, and we're going to be adding row 2. And I don't want to get in the way of my beautiful 3D planes that I've drawn here. Okay, so row 1. 1 plus 0 is 1. -1 plus 1 is 0. And 0 plus 0 is 0. So you notice by getting rid of the Z, things are super handy to deal with the rows on my way back up. And -1 plus 2 is 1. And so there it is. I have this nice bottom triangle of zeros. I have this nice top triangle of zeros. The main diagonal, which, as you said, are the coefficients of x, y, and z, are now 1. So I can see that x is 1, and y is 2, and z is 3.
Okay.
Okay? So when you're done, even if there are like nasty fractions and things like that, these are all 1.
Yeah, they have to be. Because
They have to be 1 to be in full reduced, row reduced echelon form. These might end up being fractions, or they might end up being like negative fractions and things like that. But these are all 1s. Okay, that's that.
Nice.
Does that make sense?
All good.
Okay, good. Okay, last thing. We're going to talk about, we aren't going to do examples, but we are going to talk about what the solution to these weird systems look like. So the system that we just looked like would look like 3 planes. None of them are parallel. They're intersecting in a single point. We get nice x, y, and z values for answers. Okay. We might have situations like this, though. Okay, so some of them, so actually the way I've got them drawn here, this one, there's a solution to this system of equations. And what does that solution look like? When I get done, what will I have as a solution?
That one looks like a line.
That is, yeah, that's right. That great drawing helped, I'm sure. Yes, this solution is going to look like a line. And so when you're reducing your matrix or your equation or something like that, you're going to end up with like a 1, 2, 3, 1, 2, 3, 4, 0, 1, 2, 1. These are just example values. And then at the bottom, you're going to end up with 0, 0, 0, and a 0. Okay? And so this means that you're going to wind up with that parametric solution that we looked at earlier, where you're going to set your z equal to s, and then you're going to say that y is equal to 1 minus 2s, and you're going to figure out what your x is in terms of a parametric solution. But the result is going to be a line. It's going to look like this when you're dealing with that matrix. You get to this 0, 0, 0 equals 0. So you'll have a solution where any value will solve this bottom line. Okay? So there's that situation. The other thing that's going on, if you've got this situation, and we don't need to worry about it so much, is just the fact that those normal vectors are all coplanar.
Yeah.
And so there was a little thing in one of the preambles for a preamble question from yesterday. The cross product, the dot cross product of the normals of this system of equations will result in a 0 value.
Okay.
Okay. Well, and that's because the normal vectors are all coplanar. And so if you take the cross product of 2, you get a perpendicular line. And then if you do the dot product with the third one, it's going to be perpendicular to that cross product vector, and the result is going to be 0.
Okay, I see.
Okay. So this one, you know, you don't have to, but n1 cross n2 dot n3, any combination of those is going to be equal to 0.
Okay.
Okay. If we look up here, let's just do a system of equations. So if this was x plus 2y plus 3z equals 5. So let's say that's the equation of the top plane. What would the equation of the next, give me a potential equation for the next plane.
2x
2x
plus 4y plus
plus
6z.
4y,
6z.
6z, exactly. Yeah. And then equals something.
Yeah.
If it was a 10, that was a 10, those lines would actually, or sorry, those two planes would actually be exactly the same. Okay.
Yeah, in common.
And so everything would be a solution if the two planes are lining up. And when we go to subtract these, we'd end up with 0, 0x plus 4, sorry, plus 0y plus 0z is equal to 0. Okay, if they were coincident planes. If they're not coincident planes, in other words, if they're parallel, and you can see the normals are parallel, we'd end up with some sort of weird thing like 0z equals 1.
Okay.
Okay, so the normals are the same, and we'd end up with an inconsistent solution. There would be no solution to that set of equations there. These ones are pretty obvious as soon as you see them.
Yeah. So, yeah, no, okay.
Yeah. All right. Next situation.
Would that one just be like 2 of them are scalar multiples and then the one is just not?
Exactly.
I
Yeah.
think that was in the preamble for this one, I think.
That's right. Yes. So these two would be like a scalar multiple, right? They might be coincident. They might not be. If they're a scalar multiple, they are. If one of that final D value is different, then they're parallel to each other. Pretty easy to see.
Mm-hmm.
When you get solving this one, you're actually going to end up with, like, you can solve any two planes, and they're going to solve to a line. But when you go to get that third one, you're going to wind up with 0z equals 5 or something like that. You're going to wind up with something that's inconsistent when you go solving it in the third line.
Okay.
And you need to go hunt out, say, did I miss the idea that those ones are parallel?
Yeah.
Okay. Here's our last situation, the TP. Okay. None of these normals are scalar multiples of each other. But do you remember from yesterday what was special about the normals?
For that one?
For the pup tent? They're all kind of, you could see them as being coplanar.
Oh, okay.
Okay. Maybe you can't see it, but from here it's a beautiful pup tent, basically.
Oh, no, okay.
Okay. So it's 3 planes, and they basically intersect in 3 unique lines. And those lines are parallel to each other. Okay. So you could find the solution to 2 of the planes. It would be one of the lines. In fact, you could find the solution to any 2 combinations of those planes. It would solve to lines. There is no solution to all 3 at the same time, though. Okay. So this one, you can't spot this one out of the gate. You can't just look at the equations and say, look, I know that some of them are parallel.
Mm-hmm. No,
When you go to solve this, once again, you're going to get the inconsistent situation. When you get to that bottom line, you'll wind up with 0z equals, 10 or something like that. And you're going to have to decide what you're dealing with. Anyways, this is that situation where that scalar product, the cross product generates a perpendicular vector, and the dot product with that same vector is going to generate a 0 for you.
Okay. Could you to figure out where the lines were, could you just pick 2 of the planes and intersect them, and then if you did that for all 3 of for all of the combinations, and you could just compare the lines and figure out that they are going to be parallel?
Yes, you could. Yeah.
Okay.
So keep in mind, there's more than one strategy, and when you look around at all the different textbooks, they throw out different strategies.
I'm just glad I'm starting to think of it in the sense of like what we've been doing, right? It's a new concept, so it's a bit tricky, but I'm glad it's starting to come along.
Yeah, and it's kind of neat when you get thinking about it.
Mm-hmm.
Now, there's another way to do exactly what you just said, right? So you could solve 2 of the lines, find out solve 2 of the planes, find out that line, find out the next line, find out the next line. And then the other thing that you can actually do with this one to find the direction vector of those lines is you can just take, so that this is plane 1 and this is plane 2, you can actually just take normal vector 1 and cross it with normal vector 2, and it will actually give you the direction vector for the intersection of those two planes. So you can actually take the cross product of each pair of normal vectors, and it will give you the direction vector for the line of intersection.
Okay, and you can just compare direction vectors and see that if they're multiples of each other, then.
Perfect. Yes, that's exactly right. If they're multiples of each other, then you know you've got the same direction vector and you've got this sort of situation going on. Yeah. And you'd actually get, if you did the cross product of each pair of lines here, you'd get the same direction vector. You wouldn't be able to differentiate them very well unless you tried to solve the system. So.
Okay, I see.
All right.
All righty.
Does that all make sense?
Yeah, I think so.
Perfect. Okay, well, that's it.
Is that the end?
That's the last lesson.
Nice.
Yeah. Well, you've got I guess you've got Relay for Life coming up.
I do. Today we're just about to set up his 3rd and 4th period. So.
All right. Well, that's perfect. Yeah. Yeah. So it's been good having you. We'll probably, I guess we'll see you next week. I'll probably do some review stuff if you want, or.
Yeah, that's fine with me. Absolutely.
And then we'll do do a bit of exam prep, and.
So test on Wednesday then?
We'll go with a test on Wednesday. Yeah.
And then exam. When should we expect that to be around?
So right now, what I'm saying is, if you want to do it sort of before, sort of anywhere up to the first week of June, I'm going to say you can set a date, and I'll try and come. I'll see if I can try and come and give it in person. Okay. And then after that, it'll just be during the exam time. So do you want to set a solid date? Let's say we do it like a week from the test.
So the Wednesday after the test?
Yeah.
So that would be.
So that'll give us there'll be 7 days. That'll give us 5 review days that we can go over. We can go over a chunk of calculus.
Sure.
I was thinking I'd throw out a 5-question review for each unit type thing, and maybe
that'd be great.
Put a day in between, and then we'll have the exam. If we set a solid date, then you know exactly where you're headed, and you know how to schedule your time. So.
Yeah. Okay.
All right.
Sounds good. I got it all.
Okay. Well, have a good day. It's going to be a beautiful weekend.
Yeah, it sure looks like it. Well, you too. All right. Thanks.
All right. See you, Jeff.
See you later.